Hello. Happy today to present the current and challenges with the secure partition manager. So I'm Olivier Després and present with Educard PID. We are both part of the open source software trusted firm team. So this session is a follow-up to an earlier session that was made at the LVC20. So agenda, we have a quick recap about why we are investing with EL2, Secure EL2, a brief update on the roadmap and presenting a few of the challenges in the progress that we have. And then I will hand over to specifically present about the integration of the SMMU within EL2. Just a brief, the next session, 305, is about running Opti as a secure partition on top of Hafnium. So this is a good complementary session that you can follow just after. So why so this picture shows the typical stack running into a zone. So normal world on the left-hand side and on the right-hand side. So we have the various endpoints being the kernel in the normal world, possibly hypervisor, and then the EL3 part of the EL3 monitor part of TFA. On the right-hand side, different secure partitions running on top of Hafnium, being the secure EL2 component. So as you can see, the SPM is split between SEL2 and EL3. That's a possible configuration from the FFS standard. So as you can see here, there are multiple parties, and the challenge is the different parties. In this picture, we show that so the intent for EL2 is to add normal world from different secure partitions. Secure partitions can be STE running in a VM, a bare metal platform driver running at STMU, or the model, the right-hand side, being a secure service running at 0 by layer at SEL1. So the main intents are privilege, normal world isolation. Also, the use of a standard interface among components. So as for roadmap, really, it's about delivering an open source EL3 plus CS reference firmware, leverage the Armv8 specification, and everything is hosted at trustedfirmware.org. And our goals is about implementing the FFA specification, current and iterations, about the compliance for the first spec, migration path for legacy TEs, and we are thinking about threat modeling and an ongoing work for the TFS threat. About the channel, the three next slides are about what we do with interrupt, what we're doing currently. So the first scenario is called the man. So where non-secure interrupts trigger while the secure. So for example, here, a TA is interrupted by a non-secure interrupt. So it traps FIQ to the PC. The SPM starts called manage exit sequence, and the interrupt is gathered through an hypervisor call, and the TD then ends exit, which itself hands the execution back to the normal mode. So this is described in the specification that we are currently implementing. The next one is the scenario where a secure partition is not requesting a manager, it's just preempted by an unsecure interrupt, and the execution goes to the SPM and handle to the normal world, can handle the interrupt and resume the secure world. The last scenario is about handling secret. So that's about the secret occurs. Yes.
The slides are not progressing.
Oh, really?
Oh yeah, it's probably in the
slide are you
first set
seeing?
of slides. Right now I see YSEL2 recap.
Okay. I'm at slide 9 currently.
Okay, for some reason doesn't progress here, and I see same comments from our attendees as well. Oh
okay.
Yeah, now I see some
let
change.
me try to share. Oh really?
Now it's not being shared. Now there's some change. Yeah.
Are you seeing my
now
screen?
I see secure interrupt handling slide.
So so that's the secure interrupt handling I just described. So while secure interrupt preempts the normal world and is to the secure world and in particular a secure partition. I will continue to power management scenarios. So it's about the second boot. I 10 now, power management. Madhu?
Yes.
Yeah. So that's about handling where the normal world calls the PSC CPU on service. So it's getting to the PSC and routed to the SPMC. The intent is that power management events can be routed to a secure partition at a secure partition endpoint. Similarly, for the hot plug case, normal world called the PSC CPU off, which is another event which can be routed to a secure. Then the next change we are about supporting security extensions within the EL2, so namely pointer authentication and BTI. So the intent is to use pointer authentication for instructions preventing oriented programming and BTI landpads for jump-oriented programming. We intend to have separate keys for EL3 and the SPMC. We are currently investigating another Arduino option, empty. Another challenge is about handling properly SIMD and later SV. So the idea here is to say store the context in EL3, but rather in EC and the alpha partitions. So TEs no longer have to save the incoming normal world context because it's done by the SPMC. And obviously, each secure partition or VM has its own SIMD that SPMC caters with. So there's the delegation from the EL3 to the SIMD NX context saving. And we're investigating the same for the larger vectors. And lastly, about partition, we have a model using a shim layer. So that's the secure partition on the left-hand side. The intent is to have one thin layer relaying between C and the SCLC. Partner contribution about adopting VHE, virtualization host in the secure world, such that we can get a read in the case of the SCL1, and such that the SPMC can exception return directly SCL0 service. And yeah, that's about the challenges. And now I will to Madhu to specifically talk about the SMMU V3 and the Partition.
Do you see my slides, Olivier? Okay. So let me get started. This is Madhukar. I'm part of the Trusted Firmware team in the open source group at ARM. First of all, I would like to thank you everyone for giving me this opportunity. So today's the agenda is about introduction to SMMU and specifically the need for SMMU V3 support in the Hafnium project. And I'll be going through the features supported by SMMU V3 IP as well as the driver implementation in the Hafnium project. So SMMU stands for System Memory Management Unit, and it's analogous to an memory management unit as we see in a typical CPU. It basically helps to perform address translation for a DMA request from an upstream IO peripheral. So it's basically translating from bus address space to physical address space. And as seen in the picture here, it sits between the master peripheral device and the interconnect, thereby serving the upstream master. In the industry, SMMU is also known with other names, typically IOMMU. And ARM has several versions of the SMMU IP over the past several years. And the recent and the most current one is SMMU V3. Let's take a look at a typical SMMU V3 IP. One of the most popular ones that is available to our partners is CoreLink MMU 600, which is built on the SMMU V3 architecture. And the reason why we are interested in supporting SMMU V3 in Hafnium is because it provides us with several security features. For example, it helps us with the translation from bus address space to system address space. And for this purpose, it actually uses the Armv8 or Armv7 compatible translation tables. And it also helps with the protection of the memory. It can actually allow or prohibit access from an upstream IO device to the memory. And it can also help with the isolation of upstream devices, where it can even differentiate the traffic, the memory accesses or requests from a DMA-capable upstream device. It does this with the help of private translation regimes. Let's take a look at it a little closer. So some of the important features that made SMMU V3 a good candidate to be supported in Hafnium are as follows. It provides us with stage 1 translation support, stage 2 translation support. It can support both stage 1 and stage 2, which also known as nested. And by default, it can also act in a bypass mode or in abort mode, where it can simply abort all the incoming translations or bypass them. Everything that every feature of SMMU V3 is configurable at boot time using system registers. And the behavior of SMMU V3, the way it translates is controlled through memory-based configuration structures. This makes it ideal to support a large number of translation contexts. It is compatible with Armv8 virtual memory system architecture, and it has support for both secure and non-secure streams, as well as substreams. It supports both AS32 and AS64 translation table formats. In this in the SMMU V3 driver, we are very much interested in some features that are implemented in the SMMU V3 2.3.2 extensions for the SMMU V3 IP, specifically the support for secure EL2 as well as secure stage 2 translation support. Our primary focus in implementing the SMMU V3 driver is the support in secure world, in the secure partition manager. So let's take a look at the terms context and streams, which are very much used with SMMU V3 driver. A context is basically the translation regime associated with any stream, and a stream is basically a memory traffic or transaction generated by an upstream peripheral device. Popular devices are like a GPU, or it could be a DMA. Every incoming transaction is tagged with a stream ID. This stream ID is unique for every transaction and helps us to pick up the right translation context for a transaction. For example, GPU any device can actually generate more than one stream, for example, the GPU here can generate a memory transaction with the stream ID 3, or it can generate another transaction with stream ID 4. The reason is simple. It's because we want to virtualize these devices across the various virtual machines or secure partitions that are hosted on top of the SPM. How exactly the stream ID is defined is implementation defined, and we capture this information in partition manifest. Let's take a look at the pseudo algorithm from a 10,000-foot view of how exactly the translation is implemented, is performed. By default, SMMU support SMMU supports the normal world translation, but SMMU V3.2 also supports secure stage translation. At first, we determine if the current transaction is from secure world or non-secure world. This is done with the help of a SSD bit, which is represented in an implementation-defined manner. Once the translation is enabled, we identify if we have to perform a stage 1 translation or a stage 2 translation or both of them. Everything is configurable, is based upon the stream ID. So a stream ID, it basically serves us to look as a lookup index, where we look into the memory and into a data structure, which helps us to identify how to translate the current transaction from an upstream master device. SMMU V3 has 3 sets of interfaces, which all of which are necessary for the driver to communicate with the IP, to configure it, and help us perform the memory translations, address translation. First, being the memory-based data structures. This is what helps us with the memory translation, with the address translations. And since it's memory-based, that means it can support a very large number of translation contexts. The second interface being the circular buffer queues, which help us with commands. The commands are necessary because the driver helps, through the commands, the driver requests the SMMU IP to perform things like validation or TLB invalidation or broadcast or synchronization. The other set of interfaces are the registers, system-based system registers, which are memory mapped in boot time to any particular memory mapped to the SPM stage 1. So these registers are independent for secure and non-secure instances of the SMMU V3. The SMMU V3 IP behaves as if there is an independent logical instances of secure world and secure and non-secure SMMU drivers. These registers also help us to perform discovery of the features supported by the SMMU V3 AP in the runtime. And these registers also help us to configure the behavior of SMMU V3. For example, when out of reset, what is the default behavior of SMMU V3? This is controlled by the register. We can program it to either abort or bypass every incoming transaction. Let's take a look at the limitations that in our current implementation of the SMMU V3 driver. The patches are currently in review in upstream tf.org patches code. As I mentioned earlier, the primary focus of this SMMU V3 driver was to support the secure stage 2 translations in the secure world. And typically, a secure transaction can either access memory from a normal world or a secure world. But a non-secure stream can only access memory from a non-secure world or from a normal world. In this implementation, we only support AR64 translation format, and at this point of time, we have not yet implemented stage 1 support, and hence there is no nested translation support. Also, we do not support any features related to PCIe, and there's no support for message signal interrupts or RAS handling or event handling or memory partitioning at this point of time. We are looking for upstream feedback. If someone requests any other features in SMMU V3, we'll be happy to take a look into it and implement it in the future. Thank you for this opportunity. We'll take some questions. Olivia, do you see questions in the Q&A?
I see questions in the Q&A. Yeah, there is one, is hardware supporting Armv8.4 SEL2 available? Not that I know. All the validation we do is currently on models, FVP. So that's not real hardware model only. There is another question maybe for you, Madhu. Who declares the device transaction secure, device or SMMU?
So the SSID bit is what helps us to identify whether it's a secure or non-secure transaction, and that is implementation defined. So that information is put on the bus, and SMMU interprets it. I'm not completely sure how it's implemented, but I believe it is the device that does it.
I see another one related to SMMU. Are you seeing it? Is there possible that one platform could coexist SMMU V3 and SMMU V3.2? If yes, does this impact SPM solution?
So I've seen some reference platforms, including from ARM, where there is a discussion about having two independent SMMU V3 IPs. So theoretically, it is possible that they can coexist, but we might have to make some changes to the driver because right now it doesn't. It looks for the support for V3.2 explicitly because our main focus is secure translation stage 2 support, which is only supported from V3.2 onwards.
Thank you. There is another one. Can SEL1 manage the stage 1? I presume so. Yes, that's the case. So the SPMC controls the stage 2 translations for secure partitions, and SEL1 controls the MMU, the stage 1 MMU for EL1 and SEL1 and SEL0. Indeed.
So it seems the question is with regarding to SMMU V3. Right now, we haven't yet implemented a mechanism where the secure partition can communicate to the secure partition manager about its stage 1 context. This is done with the help of something called context descriptor. Imagine it as being parallel to a stage 1 descriptor. We haven't yet implemented that, and how exactly that is done is also implementation defined.
Okay, I don't see other questions in the Q&A. Are there in the chat?
I think you have answered all the questions. I can't see any more questions. I think a lot of questions have already been answered in the chat, actually.
Great. Thanks, Achin, for supporting.
Thank you very much for the interest in the presentation.
Thanks for your participation.